Good morning. This is your stats sensei, Mr. Spensei, and this is Death Packet for means, and we will be doing problems 31 through 40 in this video. A researcher believes that a new diet should improve weight gain in laboratory mice. If the average gain for mice on the new diet is 5.3 ounces with a standard deviation of 0.5 ounces, while 15 control mice on the old diet gain an average of 5 ounces with a standard deviation zero point 0.4, where is the p-value? All right, in this particular case, we have two different groups. All right, so let's go ahead and divide them up. New and old, right? So in the new one, we have an N sample size of 12 with a X bar of 5.3 and a standard deviation of zero point 0.5. The new one, while the control or the old, and I'll just put C for control, that's probably better. Control had 15 mice with an average gain of 5 ounces. So 5 versus 5 point. So this is, and then we have a standard deviation of zero point 0.4. And just to make things a little more clear, I'm going to say this was N for the new, the sample mean for the new, standard deviation for the new. N for the control, sample mean for the control, and standard deviation for the control. All right, we can go ahead and write the formula and do all that, or we can go straight to the calculator. And since it's multiple choice, we're going to go straight to the calculator because I think that will be more efficient. That's a little disturbing and got a calculator that didn't charge. So here we go. Stat test. And we have two samples in this case. So we're going to go to two sample t-test, which is number 4. And we have 5.3 for our sample mean for the first one. 0.5 is the sample standard. Oops. Stat test. Two sample t-test. 0.5. And we have a sample size of 12. The next one, we have a mean of 5, standard deviation of 0.4, and a sample size of 15. And they want to see that the new diet should improve the weight gain. So we're wanting to have more from the new than we have control, more weight gain from the new than we have from control. So if we were writing our null HO mu new is greater than mu, excuse me, HA mu new is greater than mu control. Our HO would of course be mu new equals mu control. All right. So we need to make sure we have greater than highlighted on the calculator, which I now do. We never pool. And we end up getting a p-value of 0.05293. All right. So p-value of 0.05293. So let's write that down. 0.0529. Well, the question is it below 0.01? And the answer is no. Is it between this and this? And the answer is no. Between this and this, got to be careful, and I'll show you how to do that. When we look at this one, this is our answer. D is our answer, and here's why. 0.0500 made it the same length, and this is 0.1000. And 529 lies between 500 and 1,000. So that's what we're looking for, is where does it lie between. So our answer to the 31 is D. All right, moving on to 32. A principal is informed that among the 1,250 students in our school, the average GPA is 2.13 with a standard deviation of 0.61. With what margin of error is the mean GPA of these students known? All right. So this one this is honestly a difficult problem. Let's go ahead and write down our formula. All right. So we basically have X bar plus or minus T star S divided by the square root of N. Now, with this part right here, the T star S divided by the square root of N, that's my margin of error. And in this case, we have 1,250 students. I'm going to have to pause for just a moment as I think about this. And when we look at this, and this is what was tricking me, is we're missing some information that among the 1,250 students, we surveyed all the students. If we surveyed all the students, we don't have any error because we did a census. So because we surveyed everybody and completed the census, our answer choice is 0. There is no error because we completed a census. Remember, when we use a census, we actually know the true population mean. So we don't have, that was actually the true population mean. So we're good there. 33, 4 math majors received the following salary offers upon graduation: 48,000, 55,000, 42,000, 51. Assuming all assumptions are met, establish a 95% confidence interval for the population mean. All right, so we have a problem here. First off, this right here would be if we were using a z-test. Just happen to know that, but we're using a t-test, so we're going to have to use the formula X bar plus or minus T star S divided by the square root of N. So let's go ahead and plug that information in. Stat, test, T interval. We'll just drop, well, first off, we got stat edit, put everything in stat edit. We have 48, 1, 2, 3, 55, 1, 2, 3, 42, 1, 2, 3, 51, 1, 2, 3. And it says, and so we have 4 math majors. So there we go. That's our data. We're going to go stat test. We're going to drop a T interval on it, which is number 8. And we have data. So we're going to choose that. We have from our list, which is L1, and we want a 95%. Okay. So we have our standard deviation is 5477. Well, that didn't help us out any because we have that for all of them. So, but we also have our mean. So we have 49,000 plus or minus. We don't know T star. We'll come back to that in a moment. We know our standard deviation is 5477 over the square root of 4. All right, so that gets rid of these first 3. They're wrong because we needed to be dividing by the square root of 4. So the question is, which one of these is the right T star? So second bars, inverse T, parenthesis, 1 minus 0.95, close parenthesis, divide by 2, degrees of freedom, 4 minus 1. And we end up with 3.18. So our answer choice for 33 is E. Make sure that you have the right degrees of freedom, because what happens if I had not subtracted the 1? Second var is inverse T. If I had not subtracted the 1, well, parenthesis 1 minus 0.95 divided by 2. And if I just use the sample size, I would have gotten the other answer, and that's wrong. We have to use the degrees of freedom. So make sure that we're using the N minus 1, that degrees of freedom equals N minus 1. 34. A police department public relations salesperson claims that the mean response time to 911 call is 9 minutes. So they're saying, all right, this is the mean of 9 minutes. A newspaper reporter suspects that the response time is actually longer and runs a test with a sample mean of 9.55. So he comes up with a X bar equal to 9.55 and a standard deviation of 3. And so in this case, HO, or HO, is going to be mu equals 9, and our alternative is mu is greater than 9 minutes. All right. What conclusion is reached if the sample, right? So we need to calculate our p-value. That's what they're asking us for, because we look at these and say, oh, p-value. So here we go. Stat, test, t-test happens to be one sample, and we're using statistics this time. So our mean, the claim mean was 9. The sample mean was 9.55. The standard deviation was 3. Sample size in this size, we had 64 calls. And we look at our alternative, and it was a greater than. And we end up with a 0.0737. All right. Now, I don't like the fact that this is rounding, but it is. Say only took it to 2 decimal places. We probably should have taken it to 4. So with it being rounded, we're going to have to choose, once again, in statistics, we always have to choose the best answer. Well, 0.07 is not less than 0.01, so that's not it. The p-value is not 0.01. It's closer to 0.07. The p-value is 0.07, indicating some evidence. Yes, it has evidence, and it's actually somewhat significant, but it's not super significant, but it is significant, and that's our best answer, because the rest of these are the wrong p-values. Okay, they're not even close. The number of 911 calls per day in a small Midwestern town is noted for a sample of 60 days with X bar of this, standard deviation of this. With what degree of confidence can we assert that the mean number of 911 calls between this town is between 22.4 and 24.4? All right. So if we do this confidence interval, we have to contain these two values. So if they're not included in the values, then it's wrong. So we're going to have to be somewhere here, somewhere below, and somewhere above that number. We can be directly at 22.4. And so basically we're going to have to be, X will have to be less than or equal to 22.4. And our X will have to be greater than or equal to 24.4. Or maybe I should say our lower has to be less than or equal to 22.4, and our upper has to be greater than 24.4. Now there's some ways to go about doing this, but the easiest way, since they gave us this and we have the calculator, is just to plug in the values and see what happens. So stat, test, T interval. All right, we have a mean of 23.4. We have a standard deviation of 3.7. This is one of those times that use your calculator. We have 60. And we have a confidence level of 0.48. Hey, that 23, that's inside. It's not less than 22.4, so it can't be that one. We go to we go to stat test, we rerun it. We have all that information in there. Only have to change one thing, the confidence level to 0.90. Oop. I went too fast. Hit the button too many times. And we have 22.6 to 24.18. Oh, we're definitely below on this one. I mean, excuse me, we're that 22.6 is still in here, and so is 24.18. We're not below and we're not above. So that one's really, really close. We'll mark it just in case we don't have anything close, but I don't think that's it because it's not large enough. Matter of fact, it's just going to be wrong because it's not large enough. Then we go back and we change it to a 95% interval. All right. And 22.44, that's down here. 22.44, that contains this value. And 24.356, I'm sorry, I misspoke. 2244 is still in between, and so is 23.56. Both of those are still in between, won't work. So now we're going to go to 96, stat test, T interval, change it to 96. 22.397. 22.39 is definitely lower than 40. So that 22.397 is less than 22.4. So that part's good. And we have 24.4, which is less than the 24.403. So we have our lower value is greater and our upper value, so we contain it. All right, so we have to contain those values. So our best answer choice is D. 99 will contain it, but it's going to be too big. We want the smallest one that's just large enough. Okay, so it's a 96 percent confidence interval. All right, suppose 48 to 65 is a 95% confidence interval estimate for population mean. Which of the following is a true statement? So we are 95% confident that the true population mean lies within the interval. Okay, we don't like this one because it says the word probability. Bad word. If 100 random samples of given are picked and a 95% confidence interval estimate is calculated for each, then the mean will be 95 in 95. Wrong. It should be close to 95, but this would have to be in all random samples or in repeated random samples. All right. If it said in repeated or if we did it for all, then it would be true. If 95% confidence intervals are calculated from all possible samples of the given size M, the mu will be in 95% of these. 36, we like this answer. Let's make sure there's nothing better, but I like that one. The probability, ooh, bad word. Confidence level cannot be interpreted until after that. That's not it. All right. So that's just saying that if we did all possible combinations or in repeated sampling, 95% of the time, it would capture it. Number 37, a consumer group wants to know if an automobile insurance company with thousands of customers has an average insurance payout for all of their customers that is greater than $500 per insurance claim. They know that most customers have a zero payouts and a few have substantial payouts. The consumer group collects a random sample of 18 customers, so N is 18, and computes a mean payout of 579. So our X bar is 579.80 with a standard deviation, big standard deviation, S of 751.3. Is running a t-test appropriate in this situation? All right. Yes, it's appropriate because the population standard deviation is unknown. Well, I kind of like that answer. So that part sounds pretty good. Let's keep going. Yes, it's appropriate because the sample size is large enough so the condition that the sampling No, that's false. We don't like that. Matter of fact, the sample size isn't big enough. So you know what? If the sample size isn't big enough and we have a lot of variation, then that means it's not normal. So no, it's not appropriate because the sample is more than 10% of the population. No, there's going to be more than 18 customers. No, it's not appropriate because the standard deviation is greater than the mean. That has nothing to do with it. That can happen. No, it's not appropriate because the distribution of the population is skewed and the sample size is not large enough. How did they know it was skewed? Well, they know it was skewed because we can't have a payout less than zero, and we have a whole bunch of payouts that are really big. So it must be skewed to the right with a bunch of big payouts out here. The other thing that would have tipped us off is we have so much variation. It's not normally distributed. So E, all right? A quality inspector plans to test a sample of 40 bottles of soft drinks labeled as 20 ounces. If she finds that the mean content is less than 19.8, she will have the bottling machinery stopped and recalibrated. It's known that the machine operates with a standard deviation of 0.75. What's the probability that the inspector will mistakenly stop a machine that is delivering a mean of at least 20 ounces? All right, so here we go. First off, HO, the mean is 20. HA, the mean is less than 20. All right, well, in this case, they're telling us the mean is actually 20. And we actually know the standard deviations. It says it's known. So we have the standard deviation of the population of 0.75. This means we're working with the z-test. All right. And we want to know the probability that we're going um, to get a sample of 40 bottles. So N is 40. And we want to know the probability that our X bar is less than 19.8. All right. So Z equals X bar minus mu standard deviation divided by square root of N. So the probability that Z is less than 19.8 minus 20 over 0.75 divided by the square root of 40. I'm only writing it down this time because this is different than the t-test, but we're just going to go stat test, z-test. Mean happens to be 20 because they said it actually was. And they said the standard deviation was 0.75. The X bar was 19.8. And we have a sample of 40. And we come up with 0.0458. Our closest p-value to 0.0458 for 38 happens to be B. So 0.0456, that's our closest. All right. 39. A congressional representative serving on the Joint Committee on Taxation states that the average yearly charitable contributions for taxpayers is 112,050. So the HO mu equals 1,250. That's the claim. A lobbyist for a national church aid organization believes the real figure is lower and samples 12. So they have a sample size of 12 and comes up with a mean of 1,092. So the alternative is the mean is less than 1,000 or 1,250. All right, same numbers, but the fact that it said lower, that needs to be a less than. And we have a X bar equal 1,092 and a standard deviation of a sample of 308. Because of the standard deviation sample, we're going to use a T. So we're going to go stat test, t-test. Mean in this case, 1,250. Sample mean, 1,092. Standard deviation, 308. 12 less than, calculate. and we end up getting a p-value of 0.051. All right. Well, 0.051 falls right here between these two values. So the answer to 39 is D. All right, last one for this video, number 40. We get there. In a one-sided hypothesis test for the mean for a random sample of size 15, the t-scores of the sample mean is 2.615. Is this significant at the 5% level? How about at the 1% level? All right, so here we go. Basically, we're going to go to a different spot on the calculator. We're going to go do a TCDF, second vars. TCDF, lower bound. We ended up with a t-score. And by the way, I should draw this picture. Here's what we're doing. We're basically saying all t distributions are centered on 0. We have a TCDF of 2.615, and we're shading up to positive infinity. So lower bound, 2.615. Upper bound, 9 raised to the 99th. Degrees of freedom, 15 minus 1. Oh, and we ended up with a very small p-value of 0.0101. All right, so our alpha, we have our first alpha is 0.05. So p-value and alpha, 0.0101 is less than 500. It's significant at the 5% level. But 0.0101 is greater than 0.0100. Barely. It's barely bigger, but it's bigger. So not significant at the 1%, but significant at the 5%. Significant at the 5%, but not at the 1% level. Significant at the 5%, but not at the 1% level. So the answer choice for 40 will be B. Hope that helped. Look forward to seeing you on the next one. Thanks for watching.